Well, welcome back, statistics scholars. This is our very last topic, variability, that you're responsible for the first exam, and it is variability. Now, if you remember from our last video, our last discussion, we were covering central tendency. And again, much like our discussion of central tendency, variability is a topic that refers to one quantitative variable, like how fast can a person run a mile, or how many children do you have, right? A quantitative variable is a way that people can be different, that has a range, a continuum, from higher to lower, from big numbers to small numbers, where big numbers mean people have more of something, and smaller numbers means they have less of something. And central tendency asks the question, is there a typical score? What is the typical person like on this single quantitative variable? Variability is a different question that we can ask about a single quantitative variable. It's the idea of how spread out are people? How variable are people? All variables vary, right? We don't ask people questions about human characteristics on which people don't vary. We don't ask people, do you have DNA? How many, do you have skin, right? Because that's not something that people vary on. But different variables have different amounts of variability. Some variables vary a lot. Other variables don't vary quite as much, right? And so this is a statement that I came up with that I think is pretty funny. Variables vary to the extent that they vary. Ha ha, aren't I funny? Well, that's just the idea that some variables vary a lot. There are some variables on which people are very different from one another. There are other variables where people aren't so different from each other. The variability is low. And just like we can calculate the mean, median, and mode, and there are three different ways of wrapping our head around who's typical: central tendency, mean, median, and mode. There are different ways of numerically calculating or wrapping our head around the idea of variability, sort of different ways of defining it. And we're going to go over sort of several of those ways of mathematically estimating how spread out people are. So, concepts. Variability is the idea that scores are different. All variables have variability, otherwise they would be constants. For example, the mathematical concept of pi, 3.1416, is a constant. It doesn't vary. It doesn't vary anywhere in the universe, at least according to mathematics, right? It's a constant. Variables, on the other hand, are ideas that can vary, human characteristics that take on different variables. But the question is, how different are they? Are they tightly packed together, like the number of children people have? 1 child, 2, 3, 0, 4, right? It's not like there are people with 1,296 children. That is not a thing. There's a fairly narrow range to how many children people have, right? When we're talking about the human characteristic, how many children people have, doesn't have a very high degree of variability. There's certainly some. Not everybody has the same number of children, but it's not going to be a huge amount of variability. But then you think about something like income. Income, on the other hand, is a human characteristic that has a huge amount of variability. Some people make no money at all. Some people are actually making negative money because every month they go more in debt, right? So you can have negative income all the way up to billions of dollars a year. There's some people that are just ridiculously wealthy and they make billions of dollars a year. So there's a very high degree of variability in income, right? And variability is the other underpinning of statistics. We're gonna all those inferential statistics that we'll eventually calculate, right? We're going to focus on the mean, the arithmetic mean, but then the other sort of underpinning is the idea that people vary. People vary around the average. And the goal of social science, the goal of psychology, anthropology, sociology, is really asking, why? Why do people vary? And what we do is look for sources of variability. We look for the reasons why people are different from each other. And the goal of data analysis, and really the goal of research, all those interesting research questions like, is age related to cognitive functioning, is really asking, why do people vary? Why are people different? And let's say I ask the question, is age related to cognitive functioning? What I'm really asking, is age creating some of the variability in why people have different amounts of cognitive functioning? Is age one of the reasons why people vary? That's the whole idea behind variability, whole idea behind data analysis, and really any kind of statistics class, figuring out why people vary. And so first we have to have a way of numerically representing how much variability there is in a particular variable. And the first way I want to teach you that we can sort of get at how spread out are people. Are people super packed together, or are people super spread out? The first way we can numerically represent this idea is the simple range, the basic range, which is just the highest score minus the lowest score, right? And oftentimes we say this, scores ranged from 0 to 100. So there is a 100-point range because 100 minus 0 is 100. Or scores ranged from 1 to 7. So there was a 6-point range because 7 minus 1 is 6, right? So the range is a single number that you can calculate for your sample. So because it's a number you can calculate for your sample, that makes it a statistic, and it's just the highest score minus the lowest score. So let's look at our two examples here. Here and here. There we have our the two examples I have for you. Here we have two histograms. Remember histograms? And here's how you would calculate the range for these two examples. We take a look at both of these graphs, and we see here on the left, we have what looks like a roughly normal distribution, and it looks like the highest score is 140. And it looks like the lowest score is 60. So we have a normal distribution, a bell-shaped curve, and the range would be 140 minus 60, which would be 80. 140 minus 60 is 80. So the range is 80 points. This variable has a range of 80 points, from the highest score, 140, all the way to the lowest score, 60. Look over here for the history. So then this is my x variable. Let's say this is IQ with an average of 100. Right? Over here on the right, we have the variable of y. So this is a totally different variable. Maybe this is, who knows? Let's say this is test scores, right? And here we have a bimodal distribution. We have something with two peaks, right? Bimodal distribution. And now let's look for the range. Well, the highest score here is 140. The lowest score here is 60. So what's the range? It's 80. So these two variables here, the variable of x and the variable of y, both have the exact same range, which is meant to give you a sense of the fact that the range is a terrible way of estimating variability. It's just a really common one. We say, oh, scores ranged from 50 to 100. Scores ranged from 1 to 10. Scores ranged from 1,000 to 2,000. It gives you a sense of how things are spread out, but it only tells you about the high point and the low point. It only tells you what is the highest score minus the lowest score, because both of these distributions here have a range of 80 points. Highest score minus the lowest score, ignoring everybody in the middle. And would you look at these two graphs? Let's look at these two graphs. If we look at these two graphs again, if variability sort of asks the question, how spread out are people? Well, these two distributions here, the people are spread out very differently in this situation compared to this situation. I would say that the distributions on these two distributions are very, very different. And yet, they have the exact same range, although the range is super easy to calculate, right? It's just the highest score minus the lowest score. So we want a different way. We want something else we can calculate to get at the question, how spread out are people? Are they tightly packed together around some average? Or are they really, really spread out and super different from one another? Another way of getting at variability is to report percentile or quartile ranks. Now, we already went over percentiles and we talked about frequency tables a couple lectures back. And a percentile is simply the score at which a certain percentage of the other scores falls beneath. Like you may have taken the SAT where you found out that your SAT score was at the 77th percentile or the 26th percentile or whatever that is. And then your score, whatever it was, let's say an SAT score of 1200. And I'm just picking that out of the air. I actually don't even know what SAT is scored out of anymore. It was scored out of 1600 when I took it, way back in the dark ages, right? But let's say an SAT score of 1200 is at the 50th percentile. Well, that would mean 50% of the SAT scores fall below a score of 1,000. And oftentimes, what researchers will do to give you a sense of how spread out things are, they'll report the 25th, 50th, and 75th percentiles, which are called the quartiles, because they're separating out your data up into quarters. So let's look at the SAT as it was scored when I went to school. I believe the bottom score was 400 when I went to school, and the top score was 1600. Now, if I was going to just get the range, I would say that was a 1600 minus 400, so the range would be 1200, right? It ranged 1200 points. But what I might also report is that the first quartile was 800. The second quartile, or the 50th percentile, was, let's say, 1200. And then I may say the 75th percentile, or third quartile, was 1400. That means approximately 25% of the folks were 800 and below. 50% of the folks, 1200 and below. And 75% of the folks were 1400 and below, leaving 25% above 1400. And again, I'm just making up these numbers. But oftentimes you'll get all three quartiles reported, which are the 25th, 50th, and 75th percentiles, to give you a sense of how spread out things are. But again, percentiles and quartiles ignore people. They ignore anybody between 800 and 1200. They ignore anybody above 1400. They ignore anybody between, right? Anybody between those scores, you're just sort of ignoring them. And let's see if we can combine our knowledge from last time with our knowledge now. What would be another name for the second quartile? What do we call the score where 50% is below and 50% is above? Did you say the median? I hope so, because that's correct. Another name for the second quartile, or the 50th percentile, is the median, because that's how we define the median. But again, percentiles, quartiles, again, feels sort of just like you're estimating how spread out people are. You're picking these three scores arbitrarily. I want to know who's at the 25th percentile, first quartile, what score is at the 25th percentile, where 25% of the scores are below it. What scores at the 50th percentile, where 50% of the scores are below it? What scores at the 75th percentile, where 75% are below it, first, second, and third quartile? We're ignoring all the people in between those folks, right? Again, there needs to be a better way. And so another way of getting at it is to report what's called the interquartile range, or the mid-spread. Because one of the downsides of the range is that outliers are going to have a huge effect on the range, right? Here, let's say I added a new score. Just one score to this distribution over here. I added a 250. Adding one score of 250 radically changes the range. So that's a problem if we want a number that represents how all the people are spread out. So the interquartile range is a little better because it essentially says, give me the score that is at the 75th percentile. In my previous example, I said that was 1400. Then it says, give me the score that's at the 25th percentile. And I said that was 800. and subtract just like you would for the regular range. And in this example, that would be 600. So the middle 50% only ranges 600 points, right? The whole thing, 1600 to 400, ranges 1200 points. That would be the total range. But now the mid-spread range is only 600 points, right? So the mid-spread sort of gets around your problem of outliers greatly affecting the range. And that's what makes it better than the range. But once again, we're ignoring people. We're ignoring anybody in between these two scores, 400 to 800, and anybody above them. We're only picking these two scores and saying, I only care about the 75th and the 25th percentile. I don't care about anybody in between. It gives you a sense of how things are spread out, but again, it's ignoring people. And that strikes me as problematic. If in my research question, I'm trying to figure out what's true about all the people, right? And so I would want to use the scores of all of the people in my sample and not ignore people in between arbitrary points like the 25th and 75th percentiles. So what can I do instead? Well, what we're going to now learn to calculate is a number that represents variability. How spread out are the people? Are they super close together around some average? Or they're super far away from that average, right? We're now going to learn to calculate one number that estimates that idea. A number that once you calculate it will tell you, is there a lot of variability? People are super different from each other. There may be an average, but people are super different from it. Or are people super close together, where if you calculated the average, most people would be darn close to that average. We want one number that incorporates everybody in your sample that gets at that idea of how are people spread out. The range ignores people, percentiles ignores people, and the mid-spread ignores people. We need a number that represents variability that or how spread out things are that incorporates every single score. So let me think about what I might want. Well, maybe I want to know how different people are from the average. The average is the one number of central tendency that incorporates everybody, right? That was one of the upsides, one of the pluses of the average, the arithmetic mean. One of the plus sides is there was no loss of information. It was one measure of typicality of central tendency that incorporated everyone. Well, maybe I might ask the question, are people very different from the average? Because if everyone is really close to the average, that would mean they're not particularly spread out. Or if people are very different from the average, that must mean that they're very, very, very spread out. People are so spread out that even given an average, people are far away from the average, right? Kind of like if I had a test, and let's say I had a 100-point final, and I told you that the average was 60, right? But I told you, but not so fast. Even though the average was 60, there were scores in the zeros, there were lots of scores in the tens, there were lots of scores in the hundreds, right? There were lots of scores in the 90s. People were super, super spread out, and very few people were actually pretty close to the average. Very few people were close to the average, right? That would have a lot of variability, right? People were super spread out. Or what if I told you that on an exam, a 100-point exam, the average was 60, but everyone was super close to the average. Most people were 65 or 55. People were super close to the average. You have two very different situations here, right? And so let's start with our average, because our arithmetic mean, because that was the one measure of typicality that incorporated everyone. So maybe I might want to know, are people very different from the average, or are people super far away from the average? Because if people are close to the average, not a whole lot of variability. If people are far away from the average, a lot of variability. So maybe there's some numerical way to sort of calculate how different people are from the average. Well, it turns out in mathematics, there's a mathematical way to figure out how different two numbers are from each other. It's called subtraction. It's called subtraction. And if we subtract two numbers, we now know how different they are. So maybe we want to start there. by calculating something called a deviation score. And a deviation score is the idea that you take the average for a particular variable. Let's say it's IQ. And let's say the average is 100. If I want to know if someone is different from that average, because let's say person 1 toddles along, and they have an average of 100, they have a score, not an average, this is an individual person's score. X sub 1 means the first person who came into my data set. They had a score of 110. Well, I could turn that person's score into a deviation score by simply subtracting the average, where I would take that person's score of 110, and I would subtract the average, and I would get positive 10. That is a deviation score. It tells me how this person deviates from the average. And let's say I do that for everybody. And now I have a set of numbers that represents how each person is different from the average. And the farther away people are from the average, the bigger these deviation scores are going to be. So if I want to get at how spread out people are, whether they're close to the average or far away from the average, I need to figure out mathematically, well, how far away are they from the average? And I do that by calculating what are called deviation scores. And that is what I've done here in this example, right? Here's my data set. Here's my sample, 3, 5, 7, and 9. And let's say this is how much people love their college on a scale of 1 to 10. The first person told me 3, the next person told me 5, the third person told me 7, and the fourth person told me 9. So these are all of my X's, because how much you love your school, call it school love. How much people love their school is the X, right? How much do you love your school is your X variable. And I have 4 numbers, 3, 5, 7, and 9. And that's how much people love their school, right? And so N in this case is 4 because I have 4 people. 4 people answered my question. And if I want to find out how spread out is their house, and normally we don't have data sets of 4 people, right? You can sort of just eyeball these 4 scores and go, yeah, 3, 5, 7, and 9, I know how spread out they are. But most of the time you have hundreds or thousands of numbers, right? And you can't eyeball those. I'm just using a small data set to illustrate what's happening here. Now, if I want to know how spread out people are, how different they are from the average, I'm going to need to subtract the average from everybody's score. So the first thing I'm going to have to do is calculate the average, right? So let's do that. So to calculate the average, I take, now summation notation, here's the summation notation formula, right? That says, add up all the X's, 3, 5, 7, and 9. Well, what's 3 plus 5 plus 7 plus 9? Well, 3 plus 5 is 8. 8 plus 7 is 15. 15 plus 9 is 24. So the sum of all the X's is 24. And please feel free to have a calculator out and to check my math. 3 plus 5 plus 7 plus 9 is 24, right? What do I have to do to get the average? I now divide it by 4, and so I get an average of 6. And if I want to then figure out how each person is different from the average, I simply subtract the average from everybody's score. As a little tip, always check your average. Always check your average. That's my little tip to you. So now, my first step in sort of wrapping my head around the idea, well, how different are people from the average? Are people very different or are people close? I'm going to start with what are called deviation scores, where I subtract the average from everyone's raw score, so-called because it's not cooked yet. 3, 5, 7, and 9 is people's raw scores. That's their raw data because I haven't done anything to it yet. And now, because I'm going to subtract the average from everyone's score, I'm going to end up with what are called deviation scores, which is, and what this is called a data transformation. I'm transforming the raw scores, the raw units of, on a scale of 1 to 10, how much did you love your school? I'm transforming those raw units of how much did you love your school, scale of 1 to 10, and I'm transforming them into what are called deviation scores, which is a new set of numbers, which tells me how much each person was above or below the average. So for person 1, I took the average of 6, because let's remind ourselves that the average was 6. I take each person's score, person 1, and I subtract the average to get -3. That means person 1 was 3 points below average. They were 3 school love points below the average. Person 2, they had a score of 5. Subtract the average of 6. Now their deviation score is -1 because they were 1 point below average. Person 3, 7 minus 6. They were 1 point above average. Person 4, 9 minus 6. They were 3 points above average. And so now I have a number for every single person in my sample that indicates how far away they were from the average, from that arithmetic mean. So maybe I could just calculate the average deviation score now, because I want to figure out if people are super close to the average, or I want to figure out if they're super far away from the average. Well, if I find the average amount people deviate, maybe that will give me a sense if there's on average a whole lot of deviation from the mean, or if there's on average not a whole lot of deviation from the mean. So let me look at my equation here for the average. You remember how that is my equation for the average? Okay. Well, let me borrow it, because that's the equation for the average. And let me go, okay, well, first, I'm going to subtract the average from everyone's score, because I just did that. See how I just did that? Let me draw a circle. X minus X bar mathematically means take the average, because remember, X bar is our symbol for the sample average. Take the sample average and subtract that from everybody's score. And in our example from the previous page, that was -3, -1, +1, and +3. Why don't I just average those deviation scores? Because then what I'll have is the average amount people deviate from the average. Ooh. Do you see how I'm using average in 2 different ways now? I'll have the average amount, a person is different from that arithmetic mean, where bigger numbers should theoretically mean people are very different, and smaller numbers should mean that they're not very different. Why might that be a problem mathematically? Why would just calculating the average deviation score, which is conceptually what I want? Are people on average super far away from the mean, all tightly packed together? Like, how many kids do you have? The average amount of deviation is probably not very big for that, right? People are probably pretty close to the average because people don't have 7,000 children. Or are people super far away from the mean on average, right? Why can't I just calculate it this way? Well, the answer to the question is the amount people deviate above the mean is always going to cancel out the amount people deviate below the mean, because that's what the mean does. It balances the stuff above it and the stuff below it. So when you subtract the mean from everybody's score, well, the deviation scores are always going to sum to 0. They're always going to average to 0. Because let's look at my deviation score from the previous slide. -3, -1, +1, +3. Well, if I added those all up to get the average, because isn't that how I get an average? I add them all up. If I added those all up to get the average, -3 plus -1 plus +1 plus +3, what number would I get? And the answer is 0. And that's going to be true every single time. And because that's the nature of the average. The average is the one number that balances the stuff above it, the deviations above it, and the deviations below it. We actually did an example of that when we covered the average. You may recall that I showed you on that seesaw that 5, remember that I gave you that example where the average was 5 because there was a 14 above it and a 1, 2, and 3 below it. And the 5 was 9 away from 14, but then when you sort of looked at how different was 5 from 1, how different was 5 from 2, how different was 5 from 3, when you added up all of those differences, those were also 9. The average balances the stuff above it and the stuff below it. So there's always going to be the same amount deviating above as deviating below. But what I want conceptually is a number that gets at, is there a lot of differences from the average or not so much? And I want to sort of theoretically get at the average amount of difference, the average amount of deviation from the mean. That's what I want to get at. But I can't just straight up average the deviation scores. But that is what, in fact, this equation is telling me to do. First get the deviation scores, then average them, because that's my kidney bean. Remember that? Here, this is telling you just to average the x's. The second equation is telling you to average the deviation scores, but that will always be 0. Well, that's not useful. Why would I calculate a number that would always be the same value? That doesn't sound useful. So what can I do instead? Well, what you can do instead is calculate something called the variance statistic. It is going to be the average of the squared deviation scores. Because if you square the deviation scores, well, now there's no negative numbers, because squares are always positive. -3 squared is -3 times -3, and a negative times a negative is a positive. So if you square those deviation scores, you're no longer going to have the problem of those deviation scores always averaging to 0. And now you can sort of hypothetically, theoretically, have a number that represents how spread out are the people, because the deviation scores are how each person is different from the average. The more different people are from the average, the bigger those deviation scores are going to be. And when you square them, they're not going to just average out to 0. And so and if you average them, then you have a number that represents how spread out people are, right? Where bigger numbers, bigger variances mean people are more spread out. People are more different from each other because people are very different from that arithmetic mean. And all you have to do then is then square those deviation scores and then average them. And this is the symbol for the variance statistic. It's either S squared, because remember how you're squaring, so the symbol gets a square, and that's for a sample, or sigma squared, and that's for a population, right? So S squared is is the variance for a sample, and sigma squared, I'll draw it for you. Sigma squared is the symbol we give for the variance for a population. Now, for a population, we simply average. Ooh, see that kidney bean? We average the squared deviation scores. First, we subtract the average from everyone's scores. Because you remember how mu, see mu there? Mu is just the population average, right? If I'm dealing with a population, I subtract the population average from everyone's score. Then I square them. Then I add them up. And then I divide by n. And there's one small difference if you're doing it for a sample. If you're calculating the variance for a sample, you do the exact same first steps, where first you subtract the average from everyone's score, because that tells you how how different everybody is from the average. Then you square those deviation scores, and then you're going to add them all up, because that's how you get an average. But then instead of dividing by n, you divide by n minus 1, which doesn't make this any less of an average, but it's a corrected average. And we'll talk more about that in a few minutes. But that's the only difference mathematically. If you're calculating for a population, you use the symbol sigma squared, and you simply divide by n as your final step because this is an average. That's your last step. Divide by the total number of scores. If you're doing it for a sample, on the other hand, you use the symbol s squared, and you can put the little s sub x squared where there's this little baby x there. But all that means is this is the x variable, right? This could be height, this could be weight, this could be how aggressive you are, whatever you've defined x as the researcher. And so you've got s squared for a sample, and you still are going to be subtracting the average, but now it's x bar, because that's our symbol for a sample average. And instead of dividing by n as my final step, I divide by n, which is your total number of scores, minus 1. More on that, why we have to do that later. It's still the kidney bean, though. You still have sigma in the top and n in the bottom. And so this is still an average. What is it an average of? The squared deviation scores. It's an average of something, the squared deviation scores. And that's why I tried to point out that kidney bean to you before. Because the variance statistic, particularly if you've never seen summation notation before, can look a little scary. But all it is an average. What is it an average of? Well, first you turn everyone's scores into deviation scores, subtract the average, then you square all those deviation scores, and then you average them. Well, if it's for a sample, you add them all up and then divide by 1 minus the sample size, 1 less than the sample size, right? N minus 1. But it's essentially just an average. And you know how to calculate an average, right? You know how to calculate an average. So it's not as scary as it looks. But we're still not done. Right? We're still not done. We have one more thing we need to do. But I also just want to point out to you, conceptually, the variance is the formal definition for the variance, which I hypothetically, possibly, theoretically, prophetically, like I'm making prophecy, may appear in your future. The formal definition for the variance is the average. What is it an average of? It's the average squared deviation from the arithmetic mean. Now that sounds like big old gobbledygook until you slow down and you translate what that's saying. The variance is simply the average amount. See how that's an average? Each person is different from the average squared. That's what it is. It's the average amount of squared deviation from that original arithmetic mean. And hopefully that makes it a little less scary. The only difference with a population versus a sample is the symbol that you use. For populations, you use sigma, and for samples, you use s. And then the only mathematical difference is for a population, you use n as a final step, and for a sample, you use n minus 1 as your final step. Still an average for a sample. It's just what's called a corrected average. More on that in a few minutes. Now, what I wanted to get at, let's say we're talking about how much people love their school. And I was trying to figure out how much do people love their school, and I wanted to figure out, was it a very spread out variable, or were people super close together? And what I wanted to get at was, is there an average amount? Is there like a standard amount people are different, right? Where I could say, sure, the average is 6, but you can bet people are going to be different from that by about this amount. There's going to be some standard amount that people are different from that center point. And I have this variance statistic, which I've calculated, but I've squared things. I've squared the original units, right? If I had a scale of 1 to 10, and each point represented how much a person loved their school, but now I've squared that. So now I have squared how much do you love your school. Or let's say I'm talking about IQ. IQ is a variable that has an average of 100. But I'm like, okay, there's a range. It ranges anywhere from 60 to 160, right? Or 40 to 160, rather. Right? So 160 minus 40, so it would have a range of 120 points. But again, the range is heavily influenced by outliers. So I want to calculate something that indicates to me, are people super close to the average of 100, or are they super far away? And my variance was one way I tried to wrap my head around that, where I took everybody's score and I subtracted the average, because then that would tell me how different each person was from the average. And then I squared their deviation scores, because if I don't, my average is just going to sum to 0. And so now I have the average amount of squared deviation, IQ points. Well, what is a squared IQ point? I don't know. I kind of get a sense of what IQ is, an IQ point, 1, 2, 3. But what is a squared IQ point? What does it even mean? I want to talk in the original way I measured it. If I was talking about IQ points, I want to talk about the average amount of IQ. And are people different from the average of 100 in terms of IQ points? Or let's say I'm talking about the number of children someone has. And let's say the average amount of children is 2.1. 2.1 children the world over. But is there some standard amount people are different from that average? Like, give or take 1 child. Sure, the average is 2, but you can bet that people are going to be pretty close to the average, because let's say on average, people are only different by about 1. But I'm not talking about children anymore. I'm talking about squared children, because I squared all the deviation scores. Oh no. I want to be talking about the original way I measured it, which is numbers of whole children. So how might I turn the square back into how I originally measured it? How might I do that? Well, how I would do that mathematically is take the square root. That's right. And we essentially take the variance, the thing we just calculated, that we had to square all the deviation scores, right? And then we got the average of those squared deviation scores, but then we were in squared units, whatever that means. And so as a final step, to put us back in the original way we measured our variable, whatever our variable is, IQ, the number of children that you have, right? We now have a number that represents the standard amount people differ from the average in the original units, right? And that is called the standard deviation. And this is what I've wanted all along. This is a number that incorporates everyone, because I took everyone's score and I subtracted the average. And I took everyone's score and I squared it. And then I added up everyone's score. And then I took that number and I divided it by the total number of people, or the total number of people minus 1. And so this is a number that represents how spread out people are, how different they are from the average. Because remember, that's where I started here. I started where I tried to figure out where is everybody compared to the average. Those deviation scores, right? And what I have now is a number that tells me what is the standard amount I could expect people are going to be different from the average. And it's called the standard deviation. It's not technically an average. The variance is technically an average. This is the square root of an average, so we call it the standard amount of deviation. The standard deviation is the standard amount we could expect someone to differ from the average on a single quantitative variable, right? And I know this looks like a scary equation. I know it does. But if you just take it step by step, it's not as scary. I don't think it's scary. You just remember, you start out. You start out by finding out how each person is different from the average. Now again, this is for a population over here, where we use the symbol sigma. Just sigma stands for the standard deviation, and just S stands for the standard deviation. The variance is sigma squared, right? And the variance is S squared if it's for a sample. For populations, it's sigma, and for samples, it's S. And this should make sense to you mathematically, the reason why we use the symbols that we do, right? Because look at it this way. If this is the variance, sigma squared, and I take the square root of that variance, that is going to give me the standard deviation. right? I just said that. You take the square root of the variance, you get the standard deviation. Well, if I take the square root of sigma squared, what does that leave me with? Well, the square root and the exponent 2 cancel each other out. And so you arrive back at your original symbol. And it's the same thing with S, because again, S is just a symbol for the exact same statistic, the standard deviation, for a sample instead of for a population. So if S squared, now again, the little baby x there is just the subscript. It tells you you're dealing with the x variable. If S squared is the variance, which is all this under here, that's the variance, and I take the square root of the variance, what symbol am I left with? Well, the radical, the square root symbol, cancels out the exponent 2, and you're just left with S. Which is why the symbols are the way they are. You might be asking yourself, well, why don't we give the variance its own special symbol and make the standard deviation the square root of the variance? Like, why don't we make our own cool symbol? Let's make the variance symbol blibbity-blop and make the symbol for the standard deviation the square root of the variance. Now, that is not a real thing. I'm just playing pretend here. And the reason why we give the standard deviation its very own symbol and call the variance the standard deviation squared is because the standard deviation is what we want. It is going to tell us in the original way we measured things, which is like if you're dealing with the number of children, whole children. If you're talking about IQ points, in IQ points. The standard deviation is going to tell you the standard amount you might imagine someone is going to be different from the arithmetic mean, from that balance point called the mean. The variance is just our one mathematical step removed from that. So we define the variance in terms of the standard deviation, even though we have to calculate the variance first. And so just keep that in mind. And if nothing else, you must commit these symbols to memory. Sigma is the standard deviation for a population. S is the standard deviation for a sample. Sigma squared is the variance for a population. S squared is the variance for a sample. Makes not a bit of difference that we calculate the variance first to get at the standard deviation. We still give the standard deviation its very own symbol and then say, well, the variance is the standard deviation squared in terms of how we symbolize it. Even though we calculate the variance first and then take the square root of it to get at the standard deviation. You always have to calculate the variance first, take the standard deviation, take the square root of it to get at the standard deviation, but we give the special symbol to the standard deviation and then say that the variance is the standard deviation squared. And if that's a little confusing, I know it's a little counterintuitive, but that's the way it is. I just have to report the rules to you. One more time. In order to calculate the standard deviation, which is the number that we want, we first calculate the variance and then take the square root of it to get the standard deviation. But in terms of symbols, the standard deviation, which is our final step, gets its very own symbol, sigma for a population, and S for a sample. And then we, in terms of symbols, express the variance as sigma squared for a population and S squared for a sample. That's the way it works, folks. So, you may be asking yourself, why did we have to divide by n minus 1 for a sample? Why do I have to divide by n minus 1? And the answer to the question is this. Essentially, and I see this in your future. I see this in your future. I see being able to talk about what we're talking about right now in your own words. Again, if you use my exact words that's on this slide, that's cheating because it's supposed to be closed note, right? You got to be able to talk about this in your own words, right? Here's the reason why we had to divide by n minus 1 when we're calculating the standard deviation for a sample. And it's because here's how variability works. Remember, a sample is a small group of people that you pull from a large group of people. And remember what a standard deviation is. It's our one number estimate. It's our one descriptive statistic, because it is a descriptive statistic. It's our one descriptive statistic that allows us to summarize numerically how spread out are the people. How variable are they? Where larger numbers, larger standard deviations mean there's more spread. People are more spread out from one another. They're farther away from the average. Big standard deviations mean people are far away from the average because they're far away from each other. Small standard deviations mean people are close together. They're very near each other. They're close to the average because they're all near each other. That's the idea behind variability, and thus the idea behind standard deviation. And so, if the standard deviation is a number that represents, you can interpret it. If a standard deviation is a number that represents how different people are from the average, and then we have to think about what that means for samples versus populations. So think about it this way. A small group of people will always be less different from each other than a large group of people. Well, that just makes sense. Let's say at Pierce College there's 30,000 students, and let's say I'm measuring the average GPA, right, at Pierce College. There's going to be 30,000 different ways for people to be different from each other. And there's going to be some average GPA. And there's going to be 30,000 different deviation scores where I take all 30,000 people and I subtract the average and I have 30,000 deviation scores. And then when I square those deviation scores, I have 30,000 of them. And then when I add them all up, I was adding up 30,000 deviation scores. But now I grab a sample of only 500. Well, 500 people are going to be less spread out. They're going to be less different from each other than all 30,000 people were. And that's going to mean that the number I calculate for those 500 people is going to be systematically too small. Well, if I want those 500 people to look like all 30,000, and I do, because I always want my sample statistics to look like my population parameters, because I always am trying to make decisions about populations and those population parameters. If I want my sample to look like my population, and my 500 people are always going to be less spread out, they're always going to be less variable from one another than all 30,000 would have been, that's a problem for me if I use the same equation to calculate the standard deviation. And this is called systematic downward bias. That's the big gobbledygook phrase that represents this idea. If you use n to calculate the standard deviation for a sample and then use that number to estimate what the population standard deviation would have been, you're going to get a number that is too small. Downward means too small. And biased means that it's wrong. Remember our discussion from the mode when I said that the mode was biased. That means that the mode in a sample often doesn't look like the mode in a population. It's biased. And when we call the standard deviation systematically biased, what we're trying to say is if you use n, if you use the exact same equation to calculate for a sample as you do for a population, for each and every single one of your samples, you're going to end up with a number that's too small. If you could actually calculate the standard deviation for the population, it will be too small, systematically downward biased. So we correct for that. And we correct for that by, instead of using n in our average of the squared deviation scores, we use n minus 1 instead, because that makes our standard deviation bigger just a little bit on purpose, so that we have a number that correctly estimates the population standard deviation. And that's why. And so just keep going over this in your notes and keep going. And I would return to this portion of this lecture a couple of times and try to see if you can wrap your head around what I mean. It's this idea that a large group of people is always going to be more have more variability than a small group of people, right? 30,000 ways to be different from each other versus only 500 ways to be different from each other. And if our sample statistics are always supposed to represent our population parameters, and the samples will always be less variable than our populations, that's a problem if I use the same equation to calculate for my sample as I would have theoretically for my population. That's going to introduce systematic downward bias. Our numbers will be too small. Systematically, all samples will always have sample standard deviations that are just a little bit too small. Underestimates of what we want. And so instead of dividing by n minus 1, n in our denominator, which is the bottom part of our fraction, we divide by n minus 1 instead, because that makes our estimate just a smidge bigger on purpose. And that is why we do it. In terms of practical application, it's just, do you use n or do you use n minus 1? If I tell you that you're dealing with a population, use n. If I tell you you're dealing with a sample, use n minus 1, right? And I see a short answer question in your future that asks you to talk about this idea in your very own words. Why we use n minus 1 instead of n when we're calculating the variance statistic or the variance standard deviation. Because again, the standard deviation is the square root of the variance. And the variance is the standard deviation squared. So let's actually work through an example, right, from start to finish, to make sure we can actually calculate the standard deviation from start to finish. So here I have my two equations, and again, the only difference between them is the symbol that you use. And what I've shown you here is the symbols for the variance, right? This is our average squared deviation score, and the symbol that we use is sigma squared. This is still the average kidney bean squared deviation score. It's just for a sample, so it gets two different symbols: sigma squared for a population, s squared for a sample. And the only mathematical difference is when dealing with a population, you can just divide by n as a final step. And when dealing with a sample, you can divide by n minus 1 as a final step when calculating the variance. And now, if I wanted to turn these into the standard deviation, I simply take the square root. Because I'm taking the square root over here with the equation, I also take the square root of the symbol. And then I end up with just sigma. What do I end up with? Just s. And again, s sub x, because x is just for your information. This is the x variable. How do I know that? Well, I got a bunch of x's here. Make sense? I hope so. All right, so let's work through this example. Here's my data set, 2, 4, 6, 8. And let's say this is on a scale of 1 to 10. What's your mood today? The first person told me 2. The next person told me 4. The next person told me 6. And the next person told me 8. So I have a sample size of 4. N equals 4, because that's our symbol for sample size, N. Big Mama N. How many people were there? And so the first thing I'm going to need to do when I look up at this equation, and I'll go ahead and erase my scrawls here, and just know once I erase, I've technically got the equations for the variance. Okay. Technically, I have the equations here for the variance, but again, find the square root, you simply take the square root, and boom, you pop out the standard deviation, which is actually what we want. So now we have 2, 4, 6, 8. And so there's an average amount of mood in this group of 4 people. So how do I find the average? Well, 2 plus 4 plus 6 plus 8. So let's work that out. 2 plus 4 is 6. 6 plus 6 is 12. 12 plus 8 is 20. So 20 divided by 4 is 5, right? So 2 plus 4, so I'll do this. 2 plus 4 plus 6 plus 8 is 20. So the sum of the x's is 20, right? Right. The sum of the x's is 20. So 20 divided by 4 is 5 because that is the average. And always check your mean. So I have calculated, and I haven't told you whether or not this is a sample or a population, right? But let's say it's a sample. So I would say that x bar is 5. X bar is 5, right? Because this is the sample average. 5 is the sample average. Sure, the first person told me 2, the next person told me 4, the next person told me 6, the next person told me 8, but the average of these 4 people is 5. That is the average amount of mood in these people. So what comes next? Well, if I look at this equation, let's break this equation down. My first step in this equation, order of operations, is to do the stuff on the inside of the parentheses, right? PEMDAS. Please excuse my dear Aunt Sally. I have to do everything on the inside of my parentheses. But I have lots of x's, right? I have 4 different x's. Person 1 told me 2. Person 2 told me 4. Person 3 told me 6. Person 4 told me 8. So I have to subtract the average from every single person's score in order to properly execute this part of the equation, right? In order to subtract the average x bar from everyone's score, I'm going to have to do it 4 times. So I take 5, 2 minus 5, negative 3. 4 minus 5, negative 1. 6 minus 5, positive 1. 8 minus 5, positive 3. And to refresh your memory, these are the deviation scores because they now tell me how each person deviates from the average. I've turned raw units, 2, 4, 6, 8, into deviation scores by subtracting the average of 5 from everyone's score. My next step. Well, the next step in this equation for the variance is to square all the scores. Do you see how this equation is now telling me to square all the scores, but not the raw scores, square the deviation scores. So I got all of the deviation scores, negative 3, negative 1, positive 1, and positive 3. And now I have to square them to get 9, 1, and 9, because negative 3 squared is 9. Negative 1 squared is 1. Positive 1 squared is 1. Positive 3 squared is 9. And why is squaring again so important? Why do we have to do this step? Because if we didn't, if we just skipped straight to the adding, well, negative 3 plus negative 1 plus positive 1 plus positive 3 is 0. And so we need to do this squaring step. It's so important because all the deviation scores will always average to 0. So that's our next step, right? So now keeping track, we've done this middle part here, x minus x bar. We took everyone's x score, 2, 4, 6, 8. We subtracted 5. And now we've squared all of those. And so what's our next mathematical step? Well, now I'm going to sum them. I'm going to get the sum of these squares. Ooh. And that is what I do next. I add 9, 1, 1, and 9. And this sometimes gets its very own symbol too. 20 is often called the sum of the squares, and oftentimes it'll be SS. So they'll call this the sum of squares. 20 is the sum of all the square deviation scores. It's called SS, or the sum of squares. We're not going to return to that for a very long time, but I just wanted to point that out to you because your book actually talks about the sum of squares a little bit. And so I wanted to point that out to you. It's not central to our discussion and lecture at this point. It will return to it later, but just put that in the back of your mind, that this step, once we've added up the square deviation scores, once we've added up 9, 1, 1, and 9, which gives us 20, that it's actually called the sum of squares. But that's not what I want. That's not what I want yet. What I want is the standard deviation. So my next step is to divide by n minus 1, because I'm telling you now that this is a sample. You're calculating the statistic. So to get at the variance, you have to divide by n minus 1. Well, n was the total number of people that you had. How many people did you have? 4. So what am I going to divide 20 by? I'm going to divide 20 by 3. 20 divided by 4 minus 1. So 20 divided by 3, or 20 divided by 4 minus 1, is 6.66666666667. And this is the variance, S squared. But I'm not done. I need the standard amount of deviation. So I take the square root of 6.666666667. And so the standard deviation, S, is 2.58 if I round. And how would I interpret this then? 2.58, what does that mean? Well, I asked people on a scale of 1 to 10, what is your mood today? The first person told me 2, the second person told me 4, the next person told me 6, and the last person told me 8. And there was an average amount of mood. The average mood was 5. There was an average amount of, the average mood in my sample size of 4 people was 5. The average mood in these 4 people was 5. Give or take 2.58 points. Yeah, the average was 5, but you could expect people to be different from that average by about 2.5 points, 2.58 points. And that is what the standard deviation tells you. It tells you how much variability is there. That's the idea. And so let's say we were talking about basketball players. Let's say that we were talking about basketball players. So we're talking about basketball players. And let's say there's 2 different basketball players. Let's say there's Kobe Bryant. He's retired now, but who cares? And when I was young, Shaq and Kobe played on the same team. They both played for the Lakers, but I'm old, so that's okay. And then you got Shaq, right? And let's say Kobe and Shaq have the same average points per game. Let's say they both are averaging 20 points per game. But then I tell you that Kobe has a standard deviation of 1. Well, that would mean on any given game, you can bet Kobe is going to be, his points per game are going to be probably within 1 point. Sure, he's got an average of 20, but there's a standard amount of difference game to game to game of only about 1 point, right? So 21 point, give or take 1 point, so 19 to 21 points. There's a standard amount of deviation, meaning most games, Kobe is pretty darn consistent. All of his games are really similar to each other. But let's say Shaq has got a standard deviation of 10 points. Well, that means game to game to game, some games he's scoring 40 points, and other games he's scoring 0 points, and some games he's scoring 20 points, but man, the standard amount his games are different is huge. And that is the power of the standard deviation. It goes beyond just the average, because 2 different groups can have very different averages, or if you're talking about like basketball players, there can be very different averages, but the amount of variability might be very different in addition to there being average differences. Because you can have the exact same average, but very different spread. I'll give you a different example. Let's talk about 2 different cities. 2 different cities. Let's say city 1, let's call it Irvine. Let's say the average income in Irvine is $80,000 a year because they're just rich down there in Orange County. And let's say Newport Beach, which is another Orange County city, also has an average of $80,000. Right? But now I tell you that the standard deviation, again, these are the averages. But then I tell you that the standard deviation in Irvine is $1,000. That means most people are probably going to be within $1,000. You could expect people to be different from $80,000 by about $1,000. $81,000, $79,000. That's the standard amount of deviation. But then I tell you that in Newport Beach, the standard deviation is $10,000. Well, that means people are very different from that average. There's a lot of people that are below $80,000 and a lot of people that are above $80,000. There's more variability in Newport Beach than there is in Irvine. As an example, that is what the standard deviation tells you. Where bigger numbers mean there's more variability. More variability. Make sense? I hope so. So the bigger the standard deviation, the more spread out you know the people are. The more different from the average you know people are. The smaller the standard deviation, the less different you know the people are from each other and thus from the average. So, now, let's combine our knowledge now. Now we've got to put it all together. How do we summarize our variables? We've got to put our knowledge of normal distributions. Remember Gaussian normal distributions? The single most common way for psychological variables to be distributed is with a normal distribution, a bell-shaped curve. We got to combine our knowledge of normal distributions, central tendency, and now our brand new concept, standard deviation. And there are some things you have to know. If a variable is normally distributed, now, are all variables normally distributed? No, some are not, right? But if you have some psychological characteristic that is normally distributed, where there's one peak, one super common score, and as you move away from that score, people become less probable. And how do I know that? Well, because down here are the scores. Here I have a variable that ranges from -3 to +3. And that's the x-axis. And along here on the y-axis, I have how probable those scores are. And hey, look, 0 is super probable. 3, not so probable. -3, not so probable, right? If I have that normal distribution, if I have a normal distribution where one peak and two tails, where, again, these are people's scores, right? There's one score that appears to be the most probable. In this case, it's 0. Let's say this is how much people love beets on a scale of, again, the root vegetable, or how much people love carrots on a scale of -3 to +3, right? And most people are like, I have no strong feelings about carrots. And as you get above average of 0, people who love beets or carrots, there's just not very many people out there. And as you get people, I hate carrots, I think they're terrible and awful, there's just not very many people out there, right? That's a normal distribution. Well, let's combine our knowledge of the average. Well, the average on a normal distribution, to refresh your memory, is right in the center. On a normal distribution, the mean, median, and mode are right in the dead center, the peak. The top of the mountain in a normal distribution is right there at the center at the peak. So the average here is 0 on this particular variable. Average amount of carrot love, 0. I have no feelings, 0. I'm not a -3 where I hate them. I'm not a +3 where I just love carrots so much. No, none of that. Right, so the average here is 0, and then I tell you that the standard deviation is 1. That means the standard amount you might expect people to be different from the average is about 1 point. Sure, the average is 0, but, give or take 1 point. Are you with me so far? So if, and only if, a variable is normally distributed, then a proportion of 0.68, or 68% of the folks, are going to be between 1 standard deviation above and 1 standard deviation below. 0 plus 1 is 1. 0 minus 1 is -1. So in this distribution, 68% of all people are going to tell me, how do I feel about carrots? 68% of them will tell me something somewhere between +1 and -1. 68%, a proportion of 0.68, will be between a score of +1 and -1 on this example. 95% of people, again, on this example, again, the average here is 0. Why? Because that's just the example I'm using. If the average is 0 and the standard deviation is 1, then 95% of people, or a proportion of 0.95, will be between +2 and -2, or within 2 standard deviations. That means when I ask people, how much do you love carrots? 95% of the people, or a proportion of 0.95, will tell me somewhere between +2 and -2. So almost all the people. Now technically it's 1.96 standard deviations, but roughly 2. And 99.7%, or a proportion of 0.997, almost all of the people will be between 3 standard deviations above the average, and again the average is 0 in this example, 3 standard deviations above and 3 standard deviations below, which will leave a proportion of 0.003 left over. Only 0.003 proportion of the people will tell me something above 3 or below -3, where they're like, I love them so much, I need to tell you +5. They're just so amazing. Or, I hate them so much, I have to tell you -5. I hate carrots. Not very many people if carrot love is normally distributed. And let's do a different example to get at this idea. So let's say I have IQ. And IQ is in fact, in nature, normally distributed. And IQ has an average of 100. And because it's normally distributed, that means it's going to have a mean, median, and mode of 100 right there at the peak. And I tell you that IQ has a standard deviation of 15. With me so far? Okay, good. That means 1 standard deviation above the average would be an IQ of 115, right? 1 standard deviation below the average will be an IQ of 85. And because I know it's a normal distribution, that means a proportion of 0.65 or 65% will have an IQ between 115 and 85. And where do these proportions come from? Are they magical proportions? No. They actually come from integral calculus. Gauss, you know that guy that came up with the Gaussian distribution, which is the normal bell-shaped curve? He actually figured it out. He did integral calculus to figure out that on any distribution, 0.68. My bad. He figured out that on any variable that is normally distributed, you figure out what the average is, figure out what the standard deviation is, and you can know for sure that 68%, a proportion of 0.68 of all of the people, will be within 1 standard deviation. Will be between 115 and 85 in this example. 2 standard deviations away, above, would be 130. Two standard deviations away below would be 85 minus 15, which would be 70. And Gauss figured out that 95%, or a proportion of 0.95 of all the people, will be somewhere between an IQ of 70 and 130. And this is going to be true for all normally distributed variables. 95% of the cases will be between the score that is 2 standard deviations above, in this case 130, and the score that is 2 standard deviations below, in this case 70. And last but not least, and again, I'm not the best artist, he figured out that if you went 3 standard deviations above the average, in this case, in this example, 145, Another standard deviation below would be 55. The 70 minus 15, which is the standard deviation. A proportion of 0.997. So 99.7%, almost everyone, will have an IQ somewhere between 145 and 55. Almost everyone will be somewhere in here. 68% of the people will be between 85 and 115. 95% of the people will be somewhere between 130 and 70. And 99.7, a proportion of 0.997 of the people, will be somewhere between an IQ of 145 and 55. And it doesn't matter what. It doesn't matter what the variable is. Let's go back to this slide. On any bell-shaped curve, any Gaussian curve, any normal distribution, lots of psychological variables are normally distributed. On any normal distribution, you can count on these proportions. Because let's use a different example. Let's erase these scores down here. And let's say I have, I don't know, people's mood on a scale of 1 to 10. Let's do that again. And let's say the average is 5. And let's say the standard deviation is 2. Well, that will mean this center point here is what? 5. And what would be one standard, whoops. The standard deviation is 2. That means the center point, the peaked point, is 5, right? And then one standard deviation away would be 7, right? And 2 standard deviations would be 9. And 3 standard deviations away would be 11. 1 standard deviation below would be 3. 2 standard deviations below would be 1. Another standard deviation away would be -1. If you could say, I have -1 mood, I'm just so depressed, right? So let me draw that for you. So here I have a normal distribution in this example. And if the average is 5 and the standard deviation is 2, then 1 standard deviation away will be 7. And 2 standard deviations away will be 9. And 3 standard deviations away will be 11. 1 standard deviation below will be 3. 2 standard deviations below would be 1. 3 standard deviations below would be -1. And if it's truly a normal distribution, and you're allowed to say your mood is anything from negative whatever to positive whatever, right? And the average is 5 and the standard deviation is 2, it will be in fact true that a proportion of 0.68 will have mood scores 0.68 or 68%. Will have mood scores between 3 and 7. 95% or a proportion of 0.95 will have mood scores between 1 and 9. And 99.7% of all the people will have mood scores between 3 and -1 if you allowed them to give you those extreme scores. But that's only true if mood is normally distributed. But if it is, these proportions hold. And they're proportions that you have to memorize. And there'll be test items quizzing you on these proportions, on the proportions of a normal curve. So, the last thing that I want to ask you to put it all together. Distributions, central tendency, standard deviation. And this is a hard question. Look at these two distributions. Here we have a uniform distribution here and a normal distribution here. Because they're symmetrical, the average is here, right? And because it's symmetrical, the average is here. And my question to you now is, which one? And notice that they have the same range. 0 over here, all the way up to close to 200, 0 to 200. They're in the same basic range, right? But you have they both have an average of 100. But they're shaped very differently. And I want to refresh your memory. The standard deviation tells me, are people close to the average or are people far away from the average? And here the average is 0 and here the average is 0. Which one has the larger standard deviation? A or B? Think about it. The answer is A. Are you surprised? Well, think about it. Think about what these two graphs are showing you. These two graphs are showing you where are the people. Here, on the normal distribution, most of the people are really close to the average, right? That's our definition. On a normal distribution, most of the people are at a peak. And there are fewer people far away from the average. And so fewer people are going to have big deviation scores. Fewer people with big deviation scores, smaller standard deviation. Over here, there's a ton of people far away from the average. Yeah, there's some people close to the average, but lots and lots and lots of people are far away from the average. So this is going to have the larger standard deviation. How about this one? Again, we have two roughly symmetric distributions, which means that the average is going to be in the middle. So in both of these cases, the average is 100. X bar equals 100 here, X bar equals 100 here, and they have the same range, 60 to 140, 60 to 140, 60 to 140. But very different spread here, right? And now my question again is, A or B? Which one has the largest standard deviation? Now remember, the standard deviation is a number that tells you, are people far away from the average or are people close to the average? Big standard deviations mean people are really far away from the average. Small standard deviations mean people are close to the average. In which one of these distributions are most people close to the average? In which one of these distributions are most people far away from the average? So which one is going to have the larger standard deviation? And the answer is B. Everyone is far away from the average here, right? Sure, the average is 100, but everyone's either from 120 to 140 or 60 to 80. And so in this case, you're going to have a huge standard deviation because every single person is far away from the average. Over here in A, you're not going to have a very big standard deviation because most people are pretty close to the average. I see questions like that in your future. Now, this lecture is often where the rubber meets the road, where for a lot of people, you start to have this, oh no, there was math, there was calculation, and not only was there calculation, there were concepts. So now is the time to come get help. If you have the ability to come to Pierce and come to my office hours, please do that. If you don't, please ask specific questions in the Q&A forum so that I can address them so everyone can benefit. And do go over this lecture again if you find it confusing. It's one of the benefits of an online class is you can go over portions of it that you found confusing. And if you send me a message on the forum, do feel free to say, hey, at minute 46, you were talking about this, and I just didn't understand what you meant when you said yada, yada, yada. Right? Do feel free to reference the video directly. And the more specific your questions can be in the forum, the better I'm going to be able to help you. Right? If you go to the forum and say, I didn't understand your lecture at all, I'm totally confused and lost, well, there's not much I can do in the forum to help you out. But if you go back over the lecture and you say, hey, at this point in the lecture, minute 36.2 or 36 minutes 2 seconds, I got lost. You were talking about this, and I didn't know what you meant when you said this thing. I'm going to be much more able to help you. But do reach out for help with this at this point if you're lost or confused at all. All right, well, I'll see you next time. Yeah, this is it. This is all the material that you'll be responsible for the first exam. All right, see you soon. Oh, and I will have a video that talks about the exam. So sort of like a primer video that talks about the exam. So make sure to watch that.